Hello everyone, and I am continuing on the 642. Well, it's a different video, where in the last video, and I even have the work right here, since I just made it, we're talking about the average value of functions. And given a velocity, and if we wanted to find the average velocity, so the average unit of this function, we had to use the integral and divide by the interval we're looking at. And what we found out is that we had an average velocity and it occurred 2 times. Now, could we find the average value of velocity, say if it wasn't even a velocity graph, where in this case we use the integral in that case. Right? In this one, we're going to do something different. In general, by the end, we're going to learn what the mean value theorem is, or the MVT, okay, often denoted in the calculus world. So keeping with this problem, what if instead of the velocity function, let's say, so recall from the last video, the velocity function was negative x fourth plus 7x third minus 14x squared plus 8x. Okay. Now we're going to look at that same problem where we're going to find what's the average velocity. But rather than look at the velocity function, we're going to look at it through the distance or the displacement function. So d of t is going to be the integral of v of t. And we can do this with our knowledge of power rule. So that's going to be negative 1/5 x to the 5th plus 7/4 x to the 4th minus 14/3 x to the 3rd plus 4x squared, and then plus some value c, which we don't know. Okay. Now, we would, in order to use this function, we have to know what c is. Now, I believe we're going to say that at time 0, we were at 0 for the purposes of that. When in this problem we're looking at, it might be someone leaving from their home, going towards work or business. So at 0, you were at a position of 0. So this will imply that c is 0. So we'll actually write our actual function of negative 1/5 x to the 5th plus 7/4 x fourth minus 14/3 x to the 3rd plus 4x squared. Okay. Now, what's the average velocity? So if we wanted to find the average velocity of d of t, well, let's visualize this. And I hope I can be able to recreate this graph. Let's see here. So there's the previous problem. So we have negative 1/5 x to the 5th plus 7/4 x to the 4th minus 14/3 x to the 3rd plus 4x squared. And I don't quite know what the graph's going to look like. Let's just try doing zoom standard, zoom 6. Interesting. Okay. Now we're only looking from 0 to 4 again. So remember that we're only looking on t being an element from 0 to 4. So on 0 to 4, let's reposition this window. Let's just go 0 to 4. Let's see here. So it looks something like this. Okay. We're just going to sketch this. It's just a sketch. Of course, we have the knowledge of calculus to be able to find some more critical points there, given our velocity, knowing when the slope is 0 and whatnot. But that's not what the purpose of this lesson is, so I'm going to keep that information. We're not going to worry about it here. All right, so what's your average velocity? So average velocity here over the course of t equals 0 to t equals 4, well, since this is a displacement graph, so we're talking about this is miles and this is hours, your average velocity from 0 to 4, well, we're talking about what's the slope of this line. Because velocity, remember, is the slope of a displacement or distance graph. So to find the slope of this graph, we would have to do d of 4 minus d of 0 over 4 minus 0. which would give us, and I'm definitely going to need a calculator, and I hope we get the same answer. Remember in the previous video, we got 2.133 repeating, so hopefully we get the same thing here. So d of 4, if I see my function here, it's going to be negative 1/5 times x is 4, so 4 to the 5th, plus 7/4, 4 to the 4th, minus 14/3, 4 to the 3rd, 4 times 4 squared. What I get here is 8.53333, which is looking good because that was our change in displacement. So that matched up as it should be. Your change in displacement over 4. And I'm not plugging in 0 because all that would go to 0. And since I already know from the previous video that this is the same calculation, I would get that your average velocity is going to be about 2.133 miles per hour, which is great. Okay, so the slope of this line is approximately 2.133. Now, to help you understand this, so we found average velocity given a displacement graph now. Now remember that when we looked in the previous lesson of what was the average value of velocity on a given a velocity function, and we got 2.13 and it happened 2 times. Well, we can find that because it intersected this graph 2 times. Now, what's it mean when we're given a displacement graph? We're not talking about intersections. Since we're talking about velocity, we're talking about slopes. So the idea is that, is the slope ever, by slope, I'm talking about your average, we're comparing to average velocity, is your slope ever 2.133 along this journey of t from 0 to 4? Well, if you notice here, the slope here is at one point, it looks like along this beginning part, the slope had to have been 2.133. And it looks like, the slope's leveling out. Those, it would never happen because those are negative slopes here, negative velocities. And then as it gets in here, as it starts rising, at some point when it's rising, it might have had a slope here of 2.133 as well. And the fact that it maybe leveled out doesn't look like it did, because as it leveled out, then it reached a slope. So notice that we also got it happen 2 times. So what's the idea of the mean value theorem if we put all that together? The mean value theorem, and now I guess I kind of jumped there. So what I'm saying here is that we were able to find the average value of velocity looking through slopes or derivatives, and we were able to find average value looking through integrals. So what's the mean value theorem say? And both of them occurred several times, which we can see there and there. Now, what's the mean value theorem say? The mean value theorem, or MVP, often denoted, is that on a continuous function f of x on a region or bound a to b, we could talk about mean value theorem in terms of integrals, or we can talk about in terms of the derivative or slope, really. Okay. Where the mean value theorem with integrals is saying that your average value, your mean value, which would be the integral of a to b of f of x dx over b to a over that time, has to occur at least once in that interval in a to b. And similarly, if you're talking about average value and you're having to look at the slopes, then you're talking about f prime of b minus f prime of a over b dot b minus a has to occur at least once in a to b. Now, what's that mean in a non-math language? So non-math language would be like, say I drive from my home to El Capitan High School. Well, at some point on my drive, say, I hit a velocity, I leave my house and I'm obviously at a velocity of 0. And at some point along the drive, I average 75 miles an hour on the freeways with I drive. Well, I guess my average velocity, because of the freeways, I might hit my top speed of, say, like 75 miles an hour. My average velocity on my trip might be, I don't know, with road time, 50 miles an hour. But the idea is that my average velocity of 50 miles per hour is if I once hit 70 miles an hour, at one point in my drive, I had to have been going 50 miles an hour. And that's because it's a continuous function. I hope that makes sense. I mean, you can't just say, oh, yeah, I got to 78 miles an hour, but I never hit 50 miles an hour. That's not true because it's continuous. Every value is plausible here because it's connected. So that's what mean value theorem is saying, like in layman terms. It's basically your average value has to occur on a given time interval, regardless if you're looking at integrals to look at the function itself or to look at its rate of change function, its slope function, and that will apply as well. Okay. I hope that makes a little bit of sense. There's a math notes box that you can read and definitely maybe look at that, and maybe the problems that you're working on will help make sense of this for you too. All right. Take care. Bye-bye.